In this session, or in this module, we're going to again talk about beta and alpha, and we're going to estimate beta both using the equation and using linear regression analysis. Using linear regression analysis, we get alpha. This will end the discussion that we began in our in-class session this week on Tuesday. So we're going to go over that CAPM and estimating beta and alpha again. Beta and alpha are derived from the capital asset pricing model, CAPM. And again, just to review what CAPM is an extension of the portfolio model. In specific, what CAPM does is build on basic assumptions about the market. And here is what those basic assumptions are. The CAPM model assumes that markets are efficient. And basically what that means is markets know all information. The markets are perfect in that sense. They know all information and there are no transaction costs. And prices reflect all the information that exists. If these conditions are met, it leads to the holding of the market portfolio. And in the market portfolio, all assets are held in proportion to their market capitalization. What that means is if you have 5 assets and the market value of each one of them is 25%, then you would hold 25% in each asset. If you have 3 assets, one is worth 50%, or one's market cap is 50% of the total, and the other 2 are 25, you would hold 50% of the one asset and 25% of the other assets. This base is the basis where when you hold all the assets in proportion at their market capitalization is the rationale for index funds. And again, we're modeling one. The Vanguard 500 fund is an index fund. If CAPM is true, then this equation holds. And what this equation holds is it describes the relationship between the expected returns of an asset, and here this is asset A. So we have an asset. The expected returns of that asset equal the risk-free rate, or the return on the risk-free asset, assuming that there's assumption that there's a risk-free asset out there, and that it enters into the calculation of the expected return on asset A. So we have the risk-free rate plus beta times the expected return on the market portfolio, which is all the assets held in proportion to their market capitalization, minus the risk-free rate. Beta here is our measure of risk, and as beta increases, our expected return would increase for this asset, and higher levels of beta mean higher risk. Note here that if beta equals 1, the expected return on the asset equals the expected return on the market. If beta is greater than 1, the expected return on the asset is greater than the expected return on the market portfolio. And if the expected return on beta equals less than 1, expected return on the market portfolio is greater than the expected return on the asset, or the expected return on the asset for beta less than 1 is less than the market portfolio. Beta itself has a specific meaning or specific value. Here you see the value of beta. Beta will equal the correlation coefficient between the asset and the market portfolio times the standard deviation of the asset divided by the standard deviation of the market portfolio. Note here again that if I give you a beta, you cannot say anything about the standard deviation of the asset relative to the market portfolio. If I tell you that the correlation coefficient is 1 and beta equals 1.2, you could tell me what the relationship is between the standard deviation of the asset and the standard deviation of the market portfolio. This equation, again, can be used to estimate beta given data. We would calculate the correlation coefficient and the respective standard deviations. Also from this equation we can get alpha. And let me explain alpha in the following way. Let's start with the CAPM equation, which you see in equation 1 here. I'm going to make one simple change as we move to equation 2, and that is that we take the risk-free rate from the right-hand side of the equation and move it to the left-hand side of the equation. So that gives us equation number 2. Now let's change equation 2 and add alpha to it. And you see equation 3. Now if CAPM holds, if the CAPM market is true, alpha will equal 0. It has to equal 0 or the CAPM equation does not hold. What we are going to do is use equation 3 in estimating a linear model. Again, what we're going to do here is estimate this equation by linear equation, linear regression equation, or linear least squares. I'm going to do an example of this in Excel, and we'll see that example here. And again, we will get alpha from that linear equation or linear regression analysis, OLS, and alpha will be the constant. If alpha is positive, we interpret that as excess returns. And think of it this way. If CAPM is true, alpha should equal 0. If it's positive, then the expected return on the asset is higher than we would expect given that CAPM holds, so we call those excess returns. Here in this equation, CAPM is actually controlling for the risk of the asset. And if the risk of the asset is higher than the market, it should have higher returns. And if it has higher than its risk characteristic should lead us to believe, we will see positive alphas. Alpha is also called Jensen's alpha. And Jensen is a researcher, and he wanted to find if mutual fund managers, or the managers of mutual funds, outperformed the market. Essentially what he did was have a market portfolio, and he lined up the returns for that market portfolio against returns from mutual funds invested by managers, and estimated the equation on the previous slide. What Jensen found was there was no excess returns to mutual fund managers, and this actually disappointed those mutual fund managers or mutual fund industry, because they would make claims that they could outperform the market, or if you invested in this fund, you could outperform the market. Jensen found that there was no excess returns, which means that you could have differences in the expected returns from a portfolio, but that was just due to different risk characteristics. Other researchers have confirmed Jensen's finding, and there's pretty good evidence that most mutual funds don't outperform the market, given that risk is controlled for. More of this is described on our Readings 1. This is our just a short article on Jensen's alpha, and it's on our reading list. It's Readings 1, and it's a very, 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 very short reading. Now what we're going to do is estimate beta, and we're going to estimate beta and alpha using linear regression analysis. I'm going to do this in this spreadsheet, week 5, beta and mutual funds. It's available on the website. I'd suggest you download it and follow along. First thing I'm going to do is estimate beta using the equation here, and we're going to do that for Microsoft, Exxon, Deere, the stocks that we used last week. S&P, here's our market portfolio. So I'm going to estimate those. I will do that on the next slide. We're again going to calculate beta here. And we're going to calculate beta using this formula. that's going to require us to calculate the standard deviation. So we'll use the standard deviation function. Here's going to be the standard deviation between Microsoft, and I can just copy that formula over here to the other cells. Note here that the S&P 500 standard deviation is lower than all the assets. Other thing I need is the correlation coefficient between the asset and the market. So that will be the correlation. Do the correlation coefficient. And I'm going to want to do that between that and the S&P 500. I'm going to put dollar signs in here because I'm going to do some copying, and I want these columns to always remain the same. And there's that function. So that gives us the correlation coefficient, 0.56 or 57. Copy that over. 100% correlation between the S&P 500 and itself. And then we write beta here. So the beta equals the correlation coefficient times the standard deviation of the asset itself divided by the standard deviation of the market. And again, I'm going to put dollar signs here. So this beta for this Microsoft is 1.37. I'm going to copy that. Exxon is 0.56 and Deere is 1.05. So we've calculated the betas using the formula. Now I'm going to calculate beta and alpha using linear regression. And remember that we have to subtract our risk-free rate from all these assets to perform that linear regression. Here we have the risk-free rate listed here, and I got this from the St. Louis Fed. But this rate is an annualized rate. And what we're going to do is take that annualized rate and put it back into a monthly basis, because these are all monthly returns. To do that, we use the same formula where we took our daily returns and make annualized returns. I'm going to show that on the next slide. Here's the equation for taking a periodic return, or return for a monthly, daily period, or a weekly period for that matter, or any period, and getting an annualized return out of it. This slide comes from week one of the week 2 modules. We're going to take this formula and rearrange it so that we can get a periodic return from an annualized return, because we have an annualized return, so we want to find the periodic return from that. Here's the working through of that, and 1 is our equation from our previous slide. Equation 2 takes the 1 over on the other side. Equation 3 multiplies through by 1 over m, and here in our case m will equal 12, and then we'll get our periodic return by equation 3 and just subtracting 1 from all the returns. So I'm going to implement that now in Excel. Here again is our annualized return, and now we're going to put this on a monthly basis. So again, we're just going to implement the formula. We're going to add the annualized return. We're going to have to divide this by 100 because it's in a, we stated this in 6.06%. We want that 6.06% to be 0.006 if it were there. Raise that to 1 over 12 and subtract 1, and there we have it. Now I'm going to copy that down for the rest of the periods, and there we have it. Now we're going to use this risk-free rate in calculating the excess returns. Again, I'm going to show you the equation that we're going to estimate on the next slide and calculate those excess returns then. Here again is the equation for alpha in equation 3. We're going to subtract the excess returns from our return on the assets and the market portfolio, and then we're going to estimate this linear equation. We're going to put our excess returns over here. So I have labeled columns excess returns, Microsoft, Exxon, Deere, S&P. What each one of those columns are going to be is Microsoft return minus our risk-free rate. And here we're always going to want the column to remain the same. So I'll put that by 1, by the dollar sign by 1. Copy this over. Then copy it down. And there we have our excess return calculations. Now I'm going to estimate my linear regression. I'm going to use data analysis regression. Here's regression analysis. Okay. Our y variable will be our returns, and I'm going to do this for Microsoft. And our x variable will be S&P 500 returns. When I hit OK, there's going to be a new sheet show up down here. And there's our regression. Here, the x variable will be our beta estimate. And if you look at this, let me just go back here. Here was our estimate by formula. It's pretty close to the same thing as with our equation. They should be actually exactly the same, but numerical error may come in occasionally. Here we have it. And note that this coefficient is alpha. And it is significant, and it's greater than 1. Or excuse me, it's greater than 0. It is significant. And in this case, you would say that alpha, there are excess returns for alpha, for as estimated by alpha for Microsoft. All right. In the homework, you will do the same procedure for the other two assets, Exxon and Deere, and see if both of those assets have excess returns as well. This completes this module.